All right, one last thing I wanted to look at with the simple harmonic oscillations is the most general form for our equation, which involves a phase angle. And what this means basically is that we don't have to start with x equaling a at time equals 0, which was what we had been doing all along. We've been turning the sine function into a cosine function. Okay, and so it could be a sine function or a cosine function or any phase angle difference between them, basically, which is just a sinusoidal looking function that's been shifted by a certain percentage of one total cycle of the wave. Okay, and so the reason why we might want to use this for more general cases is we might not start with a maximum amplitude at time equals 0. You might just be activating the computer at a certain moment, and that's going to catch your sine wave function at some other point other than the maximum value in t equals 0. And so we could have initial conditions where x equals x naught at time equals 0, where x naught isn't equal to a, and v isn't equal to 0, and the acceleration isn't your maximum value, just simply because you're shifted. And so let's just look at how this would work. Let's say that we have our regular, good old x equals a cosine omega t function, looks like this. But then we, by shifting our time of measuring by 1/4 of a cycle, we could easily turn the cosine function into a sine function. Okay, and so that would correspond to shifting the cosine function by an amount that's equal to plus phi in the theta direction, or in this case it would be in the time direction, because omega t equals theta. Okay, and so if you had something like y equals x, and then you go to y equals x minus 1, that's actually a shift of plus 1 this way, because then y is 0 when x is 1. Okay, so by subtracting something from the horizontal variable, it's the same thing as shifting that function in the positive direction. Okay, and so if we have the cosine function, we shift it by an amount phi, that'd be the same as writing it as the cosine of omega t minus that angle phi. And in this case, if we're trying to turn it into a sine function, we know that the sine of an object is the cosine of its complement. Okay? So we can rewrite the sine of omega t as a times the cosine of omega t minus pi over 2. And so that then gives us this expression for the sine function. And so, or we could shift it by an amount that's equal to pi. If we did that, then it would look like this. This would be a minus cosine function. So x then would be equal to a times the cosine omega t minus pi. That would be equal to minus a times the cosine of omega t. So we could turn a cosine function into a sine function, or we could turn it into a minus cosine, turn it into a minus sine function, or we can be at any other intermediate point. And this just gives us more flexibility in where we define the displacement to be at time equals 0. Okay, it gives us a more general case. So let's say that using this expression that we have x naught not equal to a, where this is x at time equals 0, v naught not equal to 0, and a naught not equal to a max. Okay, so these would be the cosine solutions if these were equal. If x naught were equal to a at time equals 0, v naught were equal to 0 at time equals 0, that would just be this one with the sine of 0 is 0 and phi is 0. And the acceleration would be omega squared A, which is omega squared times x max. Okay, so if that's not the case, then we can write that x naught is equal to A times the cosine of phi, if phi is not equal to 0. And then V naught be equal to minus omega A times the sine of phi, and A naught would be equal to minus omega squared times x naught. Okay, and so from these initial conditions, we can determine, if we know what x naught, v naught, and a naught are, then we can determine the amplitude and we can determine the angular frequency. Okay, so that's pretty cool that we can do all of that in this more general case. Okay, so if x naught, v naught, a naught are known, we can find the phase angle, the amplitude, and omega. That's pretty cool if we can actually do that. Let's see if we can. Well, here I'm going to take x naught and v naught equations. I'm going to divide this one through by minus omega. So what I end up with then is sine phi equals minus v naught over omega. This is a times the sine of phi. And a cosine of phi is equal to x naught. So if I divide one equation by the other, I get the tangent of phi is equal to minus v naught over omega x naught. Okay, so that gives me phi if I know omega. Okay, but we do know v naught and x naught. So I'm not done yet though. I've got two other conditions. I can take these two equations, square them, and add them. So that gives me a squared cosine squared phi plus a squared sine squared phi equals x naught squared plus v naught squared over omega squared. And then I can factor out the cosine squared plus sine squared. And so that'll equal then x naught squared plus v naught squared over omega squared. But then this is 1. That's a trig identity. Cosine squared plus sine squared is 1. So a then is equal to the square root of x naught squared plus v naught squared over omega squared. Okay, so we've got now a in terms of x naught and v naught, but still we don't know what omega is. So how do we get that? Well, we get that from the third equation, because that gives us directly what omega is. So omega then is equal to, here, the square root of minus a naught over x naught. And so you might say, well, wait a minute, that's the square root of a negative number. And so that's no good. But remember that a naught and x naught have to have opposite signs. Because when you pull something this way, it's got a restoring force, which is in the same direction as the acceleration. So that automatically cancels out this negative sign, and it gives us the result that we're looking for, which is a positive value for the square root of a naught over x naught. So that can go into both of these expressions for omega and allow us to solve for phi and a. And so now we know all three of those.